x minus now, minus x omega naught squared sine omega naught t. Okay. So this is our equation number 2. This is our equation number 3. And this will be equation number 4. Hey, listen to me now. It is not that bad, okay? When deriving it, it's like, holy crap, okay? But when you're actually doing it in a problem sum, it is not that bad. Are we clear? Okay, then look at this like, oh, here we go again, okay? Same shit, different smell. No, it's not that bad. So we are going to substitute 2 to 4, okay, into equation 1. Okay, so we're going to put everything into equation 1. Okay, so what we have is, okay, I'll let you all copy first, or you know what, I'm going to copy this. Come on. Okay, so we are going to substitute 2 to 4 into equation 1. Okay, so we have minus x omega naught square sine omega naught t, right, plus k over m, and is x sine omega naught t, and then this whole term will be equal to FO over m, okay, sine omega naught t. Okay. So we know what is the common term is the what? Sine omega naught t, sine omega naught t, sine omega naught t. So we're going to drop it because left hand side has sine omega naught t, right hand side also have sine omega naught t. So this will be equal to minus x omega naught squared, okay, plus by x k over m, okay, is equal to FO over m. Okay. So x over here will be equal, or x we bracket k over m minus by omega naught square. This is equal to FO over m. Okay. So x over here will be equal to FO over m divide by k over m minus by omega naught squared. Okay. So I'm going to note. Okay, I'm going to put note that we know that omega n is equal to square root of k over m. We know that. Okay. And from here, we know that omega n squared is equal to k over m. Okay. So we can rearrange this, right? We can rearrange this. Okay, so x is equal to FO over m. Okay, so I'm going to take out k over m. Okay, so this expression over here is minus 1 minus omega naught squared multiplied by m over k, and I close my bracket. Okay. So from here, we can get rid of the mass So we come up to FO over K now, divide by 1 minus by omega naught squared over omega n squared. Then we close our bracket. So the particular solution, that is our x, right? So therefore, I think it's from equation number, wait, there was a, hold on, I'm looking for, yeah, from equation number 2, all right, from equation number 2, we know that xp is equal to x sine omega naught t, right? So this will be equal to f naught over k divided by 1 minus by omega naught squared over omega n squared bracket, and then you have sine omega naught t. So the complete solution, so therefore, x as a function of time will be equal to the transient state plus by the steady state. Okay, so some of you might say, Eugene, you start throwing a monkey wrench that terms that I don't understand. Yes or no? What do we mean by transient? What do we mean by steady state? Okay, so I'm going to show you now. So most of the time, we can draw positive or negative, either one. Okay, and this is time, and this is x. Okay, we put a certain magnitude. Okay, so let me write out the expression of the whole term. So this will be equal to C1 sine omega t plus by C2 cos omega t plus by FO over K over 1 minus by omega naught squared over omega n squared. And this is multiplied by sine omega naught t. So this term over here is the transient state. This term over here is the steady state. So when is it a transient and when is it a steady state? Okay. If we were to look at a simple condition, okay. So this is our XSS. Okay. XSS, the subset SS means steady state. Now, what I'm drawing here does not reflect on this equation yet. Okay, but I want to show you all this. Okay, so I'm going to zoom in. So this is how our system will respond. It disappears. I don't know why. Okay. So when is it a transient state? When is it a steady state? So up to here, on the left-hand side, we call it a transient state. Okay. What you see on the transient state is the amplitude is ever changing with what? time. When it's steady state, there is some changes, but it's very what? Small. Are we clear? There is some changes, but it's very small. So over here, right, there's a change in magnitude, but we will call this like steady state. Now, what this amplitude is, or XSS as a function of time, is we decide. You decide what range of amplitude is what? Acceptable. Are we clear? Okay. What sort of amplitude is acceptable? Okay. So now coming back to our problem now, to this function, as you can see, right? What will happen down here is very similar to what the one I drew before. Okay, this is just a sketch, okay? It's very similar to the one we had before. Okay, this is X. So what you will see is you will see, so let me do something illegal first. Okay, you will see this. Are we clear? Okay, so from here on, this is known as a what? Transient. And this is known as a what? Steady state. Okay. Now, a lot of theory. Okay. Let's do some an example. As I said, it is not that what? Not that bad. Okay. Okay. So let's look at now. When I draw for you, when I write for you the problem the first time, you're like, huh? It's normal. When I learned mechanical vibration the first time, I'm like, whoa. Okay. But it's not that what? It's not that bad. Okay. It's easier than statics. Am I right? No comment? Oh, shit. Right. So let's look at an example. So the example I'm going to give you is we have a beam. Okay, we have a beam. Okay, and the beam is simply supported. So at point A, what do we call that type of support? Any idea? Hey, at point A, what do we call? Pin. When it's pin in terms of X and Y, when it's spin, right? X motion is equal to 0. Y motion is equal to what? 0. On the right hand side at point B, what do we call this? Roller. When it's a roller, X is not equal to 0, but Y is equal to 0. Okay? Are we clear? Today, before you go home, how many of you pass under an overhead bridge on the highway? So my advice to you is when you go home today at about 10 o'clock, stop at the highway where you see a bridge, look under the bridge. Okay, take a torchlight and look under the bridge and tell me what you see. I'm not interested in raccoons. I'm not interested in skunk, but I'm interested in the structure. But you have to tell me what you see, okay? Now, On this structure, we are going to attach a motor. And the motor is rotating at omega naught is equal to 20 radians per second. Okay. So what is given to us is the weight of the motor is equal to 150 pounds. Okay. Now, the next term I'm going to use is called static deflection. And the static deflection, okay, is equal to 1 inch. Now, what do you understand by the term static deflection? Static deflection is caused by the weight of the motor when omega naught is equal to 0 radians per watt second. So you put your motor on a simply supported beam and you realize that you have a deflection of what? 1 inch. Okay, I'll see you tomorrow.
You know, for the other question for the calculator, I couldn't do it with the calculator, so I did it manually. Am I on the right track or did I deviate off?
Yeah, you're on the right track. Wait, sorry, yep, all right track.
Thank you, sir.
It's a dance free vibration example they did. When you're defining the time for displacement to go to zero, what ballpark should it be in? Because I kept getting big numbers.
Let me solve it first. As I said, I did not know. Really, I don't know. If I knew, I should not have done that to you guys. Okay, if I knew. Go on.